We talked about the marginal rate of substitution. That was the MRS. Now we're throwing a T in there. It's the mrTs, the marginal rate of technical substitution. Everything that we're going to do in this lecture, we've already done. The only difference is now we're translating a new interpretation for old mathematical objects, which means all the work you already put in is going to pay dividends. There's really nothing conceptually difficult here. It's just applying the ideas we've already come up with to production instead of consumption. So before, in the consumption world, we thought about the relative change in utility, or not really, we thought about how a relative change in the consumption of different goods, the trade-off between goods, affected utility. And in particular, we asked, if you want to keep the utility level the same and you just change the consumption of X by a tiny bit, what is the proportional change in Y that keeps you, the consumer, equally well off? Well, we can just replace goods with inputs equally well off with equal production, and we get this idea of marginal rate of technical substitution. How much capital would be needed to replace the lost unit of labor? For example, maybe one of your farmhands got his leg run over by a thresher, and he's now the guy just buying the right shoes. You know, he lost his left leg, now he's just buying the right shoes, and that's why the price of right shoes was higher than the price of left shoes in the previous example from like 4 weeks ago, in case you don't know what I'm talking about. So we're thinking about, if you lose a laborer, how many tractors would you need to replace that laborer? And when I say replace, what I mean is to keep production at a constant level, right? So to not have to decrease production. So this is essentially exactly the marginal rate of substitution, except instead of thinking of keeping utility constant, we're thinking of keeping production constant. So the marginal rate of technical substitution at a given point between capital and labor is the rate at which we trade off capital for labor or labor for capital, keeping the rate of production the same. So thinking about being on what's called an isoquant curve. Iso means same or one, like isotone or isometric, or probably other examples. And quant means quantity, so an isoquant is a graphical, it's the line of constant output. And if we're staying along that, we could look at what's the derivative of k with respect to L. Along that, that's the slope of the isoquant. I'll give you a graphical interpretation right now. This is what the isoquants look like. You can see each of the things that look like indifference curves are now labeled as levels of production. You have quantity 10, quantity 20, quantity 30. That's how much output you have at each level. And these are different components, different input vectors, so amounts of capital and labor that produce the same amount of output when combined, according to the firm's technology, right? So the point A has amount labor A, capital A, the amount B has labor B, capital B, but they contribute in different proportions, but end up producing the same amount if you had A and A or B and B, right? And we can see that here you're trading off A for B. You're moving down along this isoquant. You're giving up a lot of labor, but you're increasing the amount of you're giving up a lot of capital and you're increasing the amount of labor, right? So you can hire farmhands to do what the tractors were doing, or you can hire tractors to do what the farmhands were doing. And the slope of this isoquant, so the marginal change, the infinitesimal change, if we just slightly shift labor, is called the marginal rate of technical substitution at that given point, right? So that's the slope of this quantity 10 line at the point A would be the marginal rate of technical substitution between capital and labor at the point A. And just like the marginal rate of substitution, it depends on what point you are. It's not a global, these are local properties, or it's a function that takes a point and you have to tell the marginal rate of technical substitution in general will depend on what your current level of capital and labor are, what your current quantity of production is, and how you're achieving that quantity. So remember, this should look the same. I'm just switching U's for F's and K's for X's and L's for Y's. But the derivative of the production function, the total derivative when you change both K and L, is the change according to how much K you changed times how much K influenced your production, df dk, plus how much L changed times how much L influences your production, df dl. That's the total change in production. And if we move along an isoquant curve, this is identically zero. That's the definition of an isoquant curve, is a line in which you're keeping the quantity produced constant. So that means that the total derivative along an isoquant is equal to zero, that total derivative in the first line, and then we can just rearrange and we can see that the negative of dkdl, the slope of that isoquant, is given by the marginal product of labor over the marginal product of capital. This, I'm going quickly and for a point to force you to realize that I'm not going to explain this to you. You have to look at the parallel between this and what we did in the consumer side. These are the same problem, right? We're setting up something that looks exactly the same, and there's a huge benefit to that, which says all the mathematical machinery that we already employed is going to be used again, right? We don't need to think through this as if it's a different problem. We just need to think about how it applies. That same problem applies to this new scenario. So once again, as in addition to the consumer's problem, both the intuition and empirical evidence suggest that this marginal rate of technical substitution is diminishing. As I get more labor, the value of labor becomes less. If I have less labor, the value of labor becomes greater. And of course, when I'm talking about the value of labor, I mean relative to capital, right? Relative to the other inputs in the production process. So there's no notion of absolute value. Maybe there is, but the value of a laborer depends on how much capital there is, right? It's not a JavaScript coder without a computer is very useless, right? A computer without anyone programming it is very useless. So their value depends on what other inputs are around. So the idea that this is diminishing means that when there's tons of farmhands and very few tractors, if I lose a tractor, that's really costly because they were all being used in the production process. All my farmhands were running them all the time. I had different shifts on these tractors all the time, and they're getting worn out. One breaks down, that's going to really hurt my production. Whereas if I have lots of tractors and not so many people working for me, so that some of the tractors are sitting idle, and I destroy one of the tractors, that's really not very costly to the production process at all. So as I gain more farmhands, the value of each individual farmhand to that production process is diminishing relative to the value of the tractors. This does not follow from diminishing marginal productivity, and we've already established that independence between diminishing marginal productivity and diminishing marginal rates of substitution when we were talking about utilities, right? Remember that you can take monotone transformations and you get the marginal rate of technical substitution or the marginal rate of substitution would remain invariant, which means that it doesn't follow from any cardinal property of the production function, in parentheses, or utility function, and therefore it's not related to those properties. What diminishing marginal rate of technical substitution is equivalent to, as one should by now almost be able to talk about in their sleep, is convex isoquants or quasi-concave production functions. So you should be able to see the direct translation of everything we've done, right? Isoquants are indifference curves, production functions are utility functions, marginal rate of technical substitution is marginal rate of substitution, and that's already a theorem that we have, right? We're just translating it into a new language. We're not actually doing anything new mathematically. One last thing to talk about is this idea of cross-productivity. So cross-productivity measures how the marginal productivity depends on the level of other outputs, other inputs. So intuitively, this is positive. What would it mean for it to be positive? It means that as I get more laborers, the value of an additional tractor is higher, right? So if I have more people to operate the tractors, as I add more tractors, each tractor becomes more valuable to me, and therefore I get a higher marginal utility out of having that additional tractor. Whereas if I have very few laborers, I'm going to get an additional tractor, and it's going to have little to no marginal value because all my laborers are already busy doing other tasks. And you could say the same thing for the marginal product of labor with respect to capital. Notice that these are symmetric because of the symmetry between cross derivatives, partial derivatives. So one kind of interesting thing, I'll end this video with just an aside that's more of a philosophical observation or something. But in the 1800s, Thomas Malthus, you've maybe heard the term Malthusian, to mean that we're worried that humans are going to destroy the earth, we're going to have overpopulation and not be able to provide enough let me start over with this. I think I'm going off the rails a little bit. Um, Math has said that there's going to be so many people that we're not going to be able to produce enough food for those people, right? We're going to destroy our civilization by having too many people and not being able to provide more, farmland and not enough agricultural output or whatever to sustain all the people that we see. And his idea was that population growth is increasing, and as population growth increases, the marginal productivity of labor decreases, right? Because there's more people, but they're not. Each individual person contributes less and less to the output, and everybody has a fixed caloric requirement. And so as you increase people, they're producing less, but as they produce less, the caloric requirement is increasing linearly, and one escapes the other. And the sort of thing that he didn't, he's derided as like a total moron now in the modern vantage, because his prediction was flagrantly false, and sort of the reason, or one potential reason you could ascribe his error to, the error in his reasoning, is he didn't take into account this cross productivity, right? That as our technology got better, the marginal productivity of people would increase. So we have better technology that allows each individual person, even though for a fixed level of technology, individual returns to labor are decreasing. If we can make technology better at the same time, that will increase the marginal productivity of labor above what ever agricultural requirement we have. And you can see now that we vastly exceed our caloric intake if everybody was farming. Or we have very few people who are actually farming. So his worry was that there wouldn't be enough people to farm, not that the distribution of calories would be unequal, right? Which is still a problem. But so eventually maybe he's right at a grand global scale, right? Because eventually we run out of room or something. But that's because there's some place where there's some input that's actually fixed. Maybe that's room or something like that. So, I don't know what's going on now. That's it.